Welcome to Disexplainer. Today we're unpacking a really high-stakes engineering mystery. How on earth do you pump boiling hot oil through frozen mud? I mean, we're talking about one of the most audacious, technically brilliant, and honestly suspenseful feats of modern engineering. How exactly do you transport millions of gallons of blistering crude oil across an environment made entirely of fragile, ancient ice without triggering an absolute environmental catastrophe? It's a massive thermodynamic puzzle, and we're going to break down exactly how engineers solved it. To really grasp the sheer scale here, we're looking at a colossal structure stretching from the frozen north of Prudhoe Bay all the way down to the ice-free port of Valdez. That is 800 miles, or about 1,287 kilometers, of just unforgiving, brutal Alaskan wilderness. This isn't just digging a trench and laying some pipe. This is carving a lifeline through some of the most isolated, freezing, and geologically volatile terrain on the planet. And get this. Every single day, an astounding 2 million barrels of crude oil surge through this system. Think about the physical weight for a second, the fluid dynamics, the immense pressure of 2 million barrels of thick liquid continuously moving across that insane distance. It's an economic artery that demands absolutely unwavering structural integrity, because a single failure, it doesn't just mean a bad day at work, it means a massive generational disaster. Which brings us to part one, the boiling oil paradox. Okay, let's dive into this ticking time bomb of a problem that engineers had to solve on day one. The whole pipeline system faced a fundamental clash of physics. See, because of intense fluid friction as it travels, plus the underground geothermal heat right from its source, this crude oil is pushed to 60 degrees Celsius. That's a blistering 140 degrees Fahrenheit. Yet more than half of this pipeline has to safely cross deep permafrost. And permafrost is soil that has been frozen solid for thousands of years. You've basically got a boiling hot river of steel trying to cross a bridge made of ancient ice. Obviously, that's a huge problem. So let's look at part two, the threat of thaw settlement. Look, if you simply dig a trench and drop this 140-degree pipe into the permafrost, you aren't just warming up some dirt. You're triggering a complete structural collapse. It perfectly illustrates what's known as thaw settlement, a super fast four-step chain reaction that leads straight to catastrophe. Step 1, the radiant heat transfers from the steel straight into the surrounding permafrost. Step 2, the ancient ice that's basically binding that soil together rapidly melts, turning what was essentially solid rock into a soupy, unstable liquid mud. Step 3, all that solid ground support completely vanishes underneath the massive weight of the pipe. And finally, Step 4, unsupported, the rigid steel pipeline violently sags, bends, and inevitably ruptures. Game over. So how did they fix it? Enter part 3, the passive refrigerator. The really ingenious engineering solution here required elevating 675 kilometers of the pipeline entirely above the ground. The logic is simple. If you can't bury the heat, you've got to lift it into the air. And engineers accomplished this monumental task by suspending the heavy pipe on 78,000 specialized supports. Can you imagine the logistical nightmare of installing 78,000 individual pillars across hundreds of miles of frozen nowhere? But here's the catch. These couldn't just be regular steel beams driven into the mud. If they were, the heat from the pipe would just travel right down the metal and melt the permafrost at the base anyway. It would completely defeat the purpose. So the crucial point is that these supports aren't just rigid stilts. They're actually highly active natural refrigerators, known as vertical support members, or VSMs. These VSMs are entirely hollow tubes acting as massive passive heat exchangers. The technical term is thermocyclones. And inside these tubes, liquid anhydrous ammonia. They chose that specific chemical for its incredibly low boiling point. It sets up this brilliant, continuous, gravity-fed loop where heat is actively extracted from the ground just by utilizing the freezing air up above. Let's trace this ammonia cycle. When the ground temperature rises even slightly above the sub-zero air temperature, the liquid ammonia at the bottom of the tube absorbs that dangerous ground heat and instantly vaporizes into a gas. That warm gas then rises straight up the tube until it hits these aluminum cooling fins at the very top. The freezing Alaskan wind hits those fins, rapidly condensing the ammonia gas back into a liquid, which harmlessly releases the ground's heat out into the atmosphere. Then, the newly cooled liquid ammonia just runs right back down the tube to repeat the whole cycle. And the absolute best part? This incredible thermodynamic system operates completely off the grid. Literally zero electricity is required. It is a 100% passive system. By just using the natural temperature differences between the dirt and the freezing Alaskan air, these 78,000 thermosiphons act like giant heat vacuums. They're actively pumping heat out of the soil way faster than the pipeline could ever put it in. That ensures the permafrost stays completely frozen solid, providing a rock-hard foundation for the pipeline all year round, even during those slightly warmer summer months. But wait, there's more. Part 4. Surviving seismic shifts. Right when the thermodynamic puzzle was solved, nature decided to throw in another high-stakes plot twist: tectonic shifts. Keeping the pipeline from melting its own foundation? That's only half the battle. Alaska happens to be one of the most seismically active regions on the entire globe. So the pipeline runs directly across major earthquake zones, most notoriously the Denali Fault. This presents a terrifying risk. When a major earthquake hits, the ground doesn't just vibrate, it violently tears and displaces. If you have an 800-mile rigid steel tube bolted firmly to the earth, the kinetic energy of a shifting fault line is going to snap that steel like a dry twig. So they had to design a flexible zigzag layout and low-friction resting shoes. This allows the massive steel tube to violently slide around to absorb the destructive kinetic energy without buckling. Instead of building in a perfectly straight line, engineers laid the pipe in a continuous zigzag, which naturally gives it room to flex. But the real magic happens right where the pipe meets those VSM supports we just talked about. The pipeline actually rests on Teflon-coated steel shoes. So during an earthquake, or hey, even just normal thermal expansion from the hot oil, the pipe isn't locked in place at all. It slides freely. We're talking horizontal movement of up to 3.6 meters, nearly 12 feet, and it can slide vertically up to 1.5 meters. The ground can literally heave and violently shift beneath it, and the pipeline will just gracefully skate across its Teflon shoes, safely bleeding off all that massive kinetic energy. Which leaves us with a totally fascinating engineering thought experiment. Working intelligently with nature's physics, rather than just trying to fight it with brute force, might actually be the ultimate key to our future resilience. The Trans-Alaska Pipeline survives not because it overpowers the freezing cold or the shifting earth, but because it bends to it. It literally uses the freezing wind to cool its own foundation. It slides with the earthquakes rather than resisting them. As we look at the immense infrastructural challenges of our own future, it really forces us to ask, how can we design our next great marvels to work passively and harmoniously with the very forces that threaten to destroy them? It's definitely something to think about.